Welcome to the first event of the year for the RSS Edinburgh local group and also the our user group in Edinburgh. So this is no likelihood, no problem. Bayesian Stats in R. We have had a slight change of format in that one of our speakers, Jordan, has had to drop out because of a family emergency. But our other speaker is going to give a slightly longer talk, and we're going to do some fun activities before to use up the time as well. So just some housekeeping before we get started. So the toilets are out there and on the left. The fire exit is there. There are no fire alarms planned. And please keep questions for the end of the talk if that's, yep, cool. Yeah, plenty of time for questions at the end. So just a little bit about the RSS Edinburgh local group. We organise a programme of events throughout the year for anyone with an interest in statistics. They cover a range of topics related to sort of statistics, data science, etc. And if you'd like to scan the QR code, you can join our mailing list and see our upcoming events and follow us on social media as well. And Ozan is going to say something about the R group.
It's a kind of very brief about, I guess, our user group that we are operating with two other colleagues. Mike was leading for a long time. He cannot make it today, and happy to represent actually both groups on the other side of the board. So we are generally trying to organize some monthly events, like towards the end of month. Generally speaking, similar to today, like taking 1 hour or so, including 2 speakers potentially. And the main goal is basically, bringing all the, our users, our lovers together to learn from each other. So far, we have I guess last year, 6 or 7 or something, very good talks, including Neville as well from RSS. And now after this event, still the March and April is actually under plan. So if you're interested I'm happy to hear your, talk ideas about R, or happy to hear your suggestions. I guess now it is time to hand over to Chris. Yeah.
Thank you. It's a little past the parcel. So I love a quiz, essentially, and as you might have noticed, my name's Chris, and I'm the person that was listed as the person who gets to book the rooms and stuff. And so I get a bit of a free license to just have a bit of fun sometimes. So essentially, we're going to do a quiz to get you warmed up a little bit before Isabella's talk. And it's going to be a Kahoot quiz. So for those of you who haven't experienced Kahoot before, this is like a ingrainment of a British childhood. So this is going to be quite fun. So if you'd like to scan the QR code, or I'm also going to pull up a code that you can type in on Kahoot, but the QR code is probably going to be the fastest/easiest way to go about this. You don't have to take part in the quiz. If you don't have a smart device, you can also just mentally come up with the answer and count yourself right. There aren't any, well, there is raffle prizes, but that's separate. So I'll let Neville talk about that, but there's no prizes for this specifically. Yeah, okay, everyone seems to have roughly done that. So what I'm going to do is I will go over now to the Kahoot quiz, which is hopefully not going to show anything that it shouldn't. Yeah, essentially, I'm now waiting for players. Oh, scan that QR code instead. I think you just got access to edit the entire quiz by accident, but please don't do that. Yeah. Oh, okay. There we go. We're getting people in. So I think, yeah, either that or you can just go to kahoot.it. Yeah, here we go. Look at that. You'll get little people. Okay. Yeah, I think there is music that comes with it as well, but I don't know if I can get the music out, if I'm honest. That would be super exciting. Oh, here we go. Yeah, I knew there was music. Okay. I'll give it a moment so or more, because there's definitely more people in the room. Okay, everyone seems to be getting in. Yeah. Okay, we'll give it one more moment, and then we can play. Yeah, share with someone next to you. But discuss the answers quietly, because, we don't want any cheating in this room. Okay. So I'll give it 3, 2, 1. Okay, we'll start. So the first question in our Bayesian statistics in our quiz is, it's very automated, what is the defining feature of Bayesian statistics? And it's multiple choice. So you've got, it always gives the same answer as frequentist statistics. It always allows updating beliefs using prior information. It guarantees the correct answer every time, or it requires a PhD in statistics to understand. So you've got this is the timer, by the way, so I'd go hit your answer really quickly. Okay, lots of people got the right answer. Nice. Okay, I'm glad we didn't think it was D. That would be not doing so well. Okay, so far, ooh, you get ranked on how fast you hit the answer as well. So yeah, maybe don't wait for me to read everything out. Okay, so which R package is most commonly used for Bayesian modeling? Is it ggplot2, rstan, dipler, or tidy models? It's subjective slightly, but yeah. Okay, most people went rstan. We've got a bit of diversity in answers. That's what we like. Okay. The third question is, if your Bayesian analysis says there's a 90% probability your model parameter is greater than 0, what does this mean? Is it there's a 90% chance you're a Bayesian wizard, your parameter must be exactly 0, your prior was wrong, or the data suggests strong evidence for a positive effect? I do love this. This is just a good vibe. Okay, most people got this. So the data suggests strong evidence for a positive effect. There is also potentially a 90% chance that you're a Bayesian wizard, but those things might be independent, so we're not too sure. Okay, so our 4th out of 5 questions is, what would a prior distribution on an unknown parameter represent? Is it a wild guess with no mathematical basis, the final estimate after Bayesian updating, a mathematical way to express prior knowledge or uncertainty, or the data set you're analyzing? There's only 5 questions, by the way, don't worry, you don't have to stand me for much longer. Okay, yeah, fantastic. I feel like everyone in the room maybe knows a bit about Bayesian statistics, so this is good, you're in the right place. Okay, and the final question of tonight is, what's a fun way to describe Bayesian statistics? Is it A, the gut feeling, the art of combining your gut feeling with cold, hard data? Like seasoning and cooking, too much or too little changes everything? Magic that turns priors into certainties, or a great way to sound fancy at dinner parties? Oh, well, you might be onto something there. So yeah, every answer here was correct. They are all fun ways to describe Bayesian statistics. There we go. So I think the winner, again, there isn't any prize, but I guess this is Reese. Okay, there you go. Well done, Reese, and David and Tess as well. So yeah, thank you, everyone. Okay, so that was just a little bit of a, I guess, an icebreaker, a warmer-upper, because now we're going to move on to Isabella's talk, who is our sort of guest star of this evening, and I guess the proper stats content. Not that that wasn't proper, I'd actually call that very proper. But yeah, essentially, I'll pass now over to Isabella, who is going to give what I believe will be a wonderful talk.
Actually, this was a really fun exercise because it gave me a really good idea of the Bayesian knowledge in this room. And I would say you've all passed. Thank you very much. So quite a lot of my work here is done already. What I want to talk about today is about a way to do Bayesian inference without a likelihood. And that might be scary, but we'll get through it one by one. So the question, are you ready for ABC? And ABC here stands for Approximate Bayesian Computation. My name is Dr. Isabella Deutsch, and I'm currently a data scientist at Smart Data Foundry. We are based in the Edinburgh Futures Institute, and we work with banking data for financial data for social good. And thank you very much, both the RSS and Edinburgh User Group, for inviting me here today. So what I want to speak about in this talk is about my Bayesian world. I have just finished my PhD from the University of Edinburgh, and that was in Bayesian statistics, because to be honest, I quite love it. I think it's a really neat way of doing statistics. And on the last answer and the last question you had, I clicked D because I think it's a way to sound fancy at dinner parties. So we're going to speak about my Bayesian world. I'll give you an example about point processes. That is something that I've looked into in my PhD thesis, and I think it's a really interesting type of model because it requires or deals with a particular type of data. And we'll see what problems we encounter there that allow us to be solved with approximate Bayesian computation. And then actually we'll look at what ABC means in practice. So we're not just going to look at this from an academic point of view, but how can you actually do this? So let's talk about the Bayesian world. Bayesians love posterior distributions. So on the left, what you can see here is a posterior distribution. It's the posterior distribution of a parameter giving our data that we have observed. And it is the prior times the likelihood. And obviously, if we want the posterior distribution to be a proper posterior distribution, proper distribution, we need to normalize it to make sure it sums to 1. So we divide by this ugly integral. And quite often, this ugly integral means we can't actually evaluate the posterior distribution because this integral is difficult. Actually, in a whole lot of cases, that's completely okay because we've learned, we've developed so many great tools that we can work, for example, with a proportional posterior distribution. Basically, just taking the top part and ignoring that constant on the bottom. And that's great. That allows us to do all the fancy sampling techniques that we have. We've more or less solved this. Well, we've not solved it completely. There's a whole lot of great researchers who do research on just that. But that is a problem that we are quite comfortable with. And what that requires us to do is that we need to be able to evaluate the prior and evaluate the likelihood. But what happens if we can't evaluate the likelihood? So if we can't evaluate that second part, things become harder. And it turns out that sometimes we can't evaluate the likelihood. We just can't do it because there's integrals in there that we can't solve. There are other cases as well where we potentially could do it, but maybe it involves a whole lot of programming and thinking and figuring out how to do it, or maybe it is computationally incredibly expensive. We just lump all of this together and say, that part we can't evaluate, and things become harder. So when we have observed our data y, we want to draw inference on our underlying parameter theta. And there is a really, I find, intuitive way of dealing that. And that is to do inference through sampling. It all starts with a really simple assumption. And that is that if we have two data sets that come from the same data generating process, and the two data sets are similar, then probably the parameters that generated those two data sets are also similar. Like, that's not rocket science. If we have samples from two normal distributions with the same variance, and they're about the same, then probably their means are quite similar. Like, that is not difficult. This hides a lot of things. What does close mean? You'll see that. We'll talk about that later. But this intuitive idea holds, like, we feel quite comfortable with that. So we can use that to do inference through sampling. So if we generate a synthetic data set y star from a parameter theta star, and that new y star is close, whatever that means again, to our original data set, we say we accept that theta star as a draw from the posterior distribution. And it turns out that approximates the posterior distribution of theta quite well. Now, when I encountered this during my master's, I thought this was like magic. This is so straightforward to understand. All we need to do is sample a data set, see if it's close, and we're good to go. And I think it's a really cool way of doing statistics. It's maybe not always as simple as it sounds here, but we can see what we can do with that. Let's get into my example that I want to lead you through here of why we need approximate Bayesian computation. And that has to do with point processes. Point processes is something that you might or might not have encountered. Probably you've heard of a Poisson process maybe once or twice before in your life. What makes a point process special is the type of data that it allows us to model. And that is when we have event times and maybe covariates. And it turns out that a lot of the data that we as a humanity, as society collect actually comes from this particular type of data. This is data where we record the occurrence of events. So when did an event happen? For example, when did a call reach a call center? I don't know why call centers are always the examples in a textbook, but we'll keep it here. So we record when did that call arrive? That is our main data structure. So you can imagine one call, one line in your data table or data frame. We can record maybe how long they were waiting for the call we answered, who took that call, what the call was about, all those things. Those are covariates that we can also record. But the main type of information that we get is when did an event happen? And we as a society record this quite a lot. The other example that we're going to talk about later as well a little bit are earthquakes. Again, we record when did an earthquake happen. This slightly differs from time series. Time series are things that are always there, and we just happen to measure it at certain points. You hopefully always have a blood pressure, but we might measure that at certain points in time. This is slightly different. So here we talk about when did the events happen. And I think it's a really interesting type of data that we sometimes try to mush into a time series, but quite often it might need its own treatment. So let's talk a little bit math about all the things that I just said with intuition. So we have these event times, and we can have a simple counting process. N of t tells us how many events happen between 0 and t. We've got this homogeneous Poisson point process. You've probably encountered this again. You would encounter that in an undergrad stats course. If you want to know the probability that an event happened in exactly that period from 0 to 10, we've got one parameter lambda. And the expected number of events to happen in a period of length t is exactly lambda. So that tells you the higher lambda, the more events we expect to happen. Okay, so if we think back to our call center example, it's not so reasonable to assume that the rate of arrival of events, that is what lambda tells us, is constant over the course of the day. At 3 a.m., probably not that many people call, I don't know, John Lewis customer helpline. I don't know. It's much likely that there is some fluctuation of arrival of events throughout the day. And we can model that, for example, with an inhomogeneous Poisson point process. So now, instead of lambda being just one parameter, lambda is a function of time. And not a lot of things change. Instead of just having the length of the interval times t, the expected number of events is now just the integral of our intensity function, as we now call it, between 0 and t. So lambda is our intensity function, and it tells us about the rate of arrival of our events in our point process. So this is all fun and neat. How we make this special is by giving our intensity function, our lambda of t, our lambda of time, an interesting parametric form. And that is what we're going to do now, because we will be talking about Hawkes processes. Hawkes processes are named after, I think, a scientist in Bristol. He's still alive, so this is not a really old model. And they are used to model events when they occur in clusters or bursts. And it turns out, again, that quite a lot of the things that we do have this type of self-exciting behavior, as we call it. You can think of the earthquakes. When one earthquake happens, it becomes likely for another earthquake to happen soon after, the aftershocks. But it turns out there's actually a huge variety of papers that showcase how you can use this type of Hawkes process to model, for example, accidents on a motorway. We have bat migration patterns. We have terrorism and other, I think, theft that all follow this type of behavior, that when one event happens, it becomes a little bit more likely for other events to follow suit. Now, if we think about what do you want an intensity function to look like that encompasses exactly this type of behavior? Well, it should look something like this, hopefully. So we've got our intensity function on the y-axis and our time on the x-axis. And whenever an event happens, here indicated by the T1, T2, T3, we want to make it more likely that other events happen soon. So we want a spike. We want the intensity function to go up. You can already feel if this goes up and up and up, we end up with an infinite number of events, or something weird's going to happen. You can already probably feel it tingling. We want this to decay again. So whenever an event happens, we get an increase in the intensity, but this should ebb off, or this should ease off at some rate again. So this is, hopefully I've convinced you that something that looks like this does indeed represent a self-exciting process that I've described earlier. So let's put a parametric form do just that. We call this now a conditional intensity function. And this is as difficult as it's going to get formula-wise in this talk. It is like 6:30. So we've got a couple of things that we want to talk about here. First of all, we have something interesting. Suddenly, the intensity function not only is still a function of time, But it now also depends not just on a parameter, but also on all events that happened previous to time t. Then we have something boring, the non-exciting part, really figuratively speaking, which is the background rate. This can capture everything that is seasonal, that is not due to this self-exciting behavior, but things like day of the week, or is it a Christmas period? Whatever you want this to be, this is what we call the background rate. Turns out in quite a lot of examples, we can also set this to a constant mu. And what we then have is the second part here, this sum. So what this means is that at time t, every event that happened previous to time t gets to contribute a little bit to the intensity function. And how much it gets to contribute is driven by two things. First of all, we have the influence kernel. This tells us how quickly does the influence decay. So quite often, simple exponential kernel will do. You can get very fancy here. You can have, there's papers written just about this part of this formula. But for now, we'll stick with an exponential one. And then we also have the influence magnitude. This is this k. This lives between, well, it could also be 0, but then would be quite a boring thing. It has to be smaller than 1, otherwise we see this exploding thing happen again. So the point that I want to drive home here is that at time t, each event that happened previously gets to contribute a little bit to the intensity function, because this is the thing that's going to bite us later down the road. Okay, so we have this univariate Hawkes process. Pretty cool thing. I did a whole PhD on this, so you can do a lot on that. The issue is that when we work with real-life data, we quite often encounter the issue that we have missing data. And that might be in the earthquake example, for example, that seismographs fail to detect earthquakes after big earthquakes have happened because they're completely out of sync. There is, I think my favorite example is about a terrorism database that is really well established. It's going on for, I think, since the 50s. But they used to record the terror attacks that happened on physical index cards. And a few of them went missing. So therefore, we have this type of data that does follow this Hawkes processy type of behavior, but we have missing data. So for example, we could see that there is a gap in the data. And to make things easier, we're going to assume that we know when the gap starts and we know when the gap ends. In the index card example, well, we know when index cards were there and there's a few missing. So this is an assumption that you could easily relax, introduces complexity, but for now, let's stick with these being known. So all what this says here is there's a gap in the data, and we make it a little bit fancy by saying we introduce this function h that goes to 0 when we are in this gap. So we've got those two things. We have the Hawkes process, somewhat complicated. We've got a gap in the data, not very complicated. But it turns out that together, those two things actually cause quite a big issue. Because when we write down the likelihood for a Hawkes process with missing data, we run into the issue that this likelihood becomes intractable. Because we've just talked about the fact that at time t, each event that happened previously to time t gets to contribute a little bit to the intensity function. And the issue is we don't know how many events happened before time t, because they might have happened in a gap, and we don't know where they were. And because of all this self-exciting nature, it becomes you can't just integrate out all of these things. This becomes intractable. And I find this quite interesting because I read a lot of ABC literature, and quite often you would find a little bit contrived examples where you could actually compute the likelihood, but we're just going to show you in a little toy example what would happen if we didn't. And this is actually a case where we truly have an intractable likelihood. But we would still like to do some posterior distribution estimation, even when we have missing data. And this is where ABC comes in and is the solution. So let's remind ourselves what we're going to do. We have this assumption that if two data sets are close, probably their generating parameters are close. And the idea is that we generate a whole lot of synthetic data sets from parameters, and the data sets that are close to the original data sets. These parameters are a good estimate of the good approximation of the posterior distribution. that is what we're going to do. So now there's one requirement, and that is that we need to be able to generate a synthetic data set without the need to evaluate the likelihood. And it turns out in quite a lot of cases, you can actually do that. And this is also the case in this very example. So what we're going to do, we are going to generate data from a Hawkes process. We're going to set the background rate to a constant. We're going to use as a background kernel, we're going to use this, the exponential decay. Very typical choices, all good. We can generating this data easy. A lot of clever people have figured out how to do that. And then we're going to distort the data. Well, that's easy. We just have to take all the data that happened in our gap and throw it away. So this is how we sample from our data generating process. And this is quite simple. And at no point requires the likelihood of the whole Hawkes with missing data. And then we're going to accept or reject the parameter that generated the data set. And now we're going to actually get into the nitty-gritty details of what it means for two data sets to be close, because this is actually where it got really difficult for me, my PhD research. Because it turns out that there is a lot of scientific literature out there that says, oh, if you've got sufficient statistics, then all of this is super easy. But if you've got sufficient statistics, you've got a likelihood, you don't need to do any of this faff. So coming up with a way to actually compare two data sets is quite tricky. So what I have come up with through mostly quite tedious simulation exercises, and to be honest, is to come up with 7 summary statistics that I think give a good representation of our data sets. And if all of those 7 summary statistics, each and every one of them is similar enough, then we'll accept the parameter as a draw from the approximate posterior distribution. And now I'm going to show you what I mean that these were a little bit difficult to get to, because the first one, okay, the logarithm of the number of observed events. I think we could all agree that sounds like something that is relevant to comparing a data set. Okay, we're going to get a little bit more obscure bit by bit. We've got the Ripley's K statistics. That just tells you how many events on average fall in a window after an event happened. Again, you could probably feel quite comfortable with that. We've got this self-exciting behavior going on. You'd want something like that. Then we're going to get rogue. We have the inter-event times, so just the times between events with a little bit of corrections for the borders. We want to take their median and divide that by their mean. You can feel maybe that this has something to do with the rate of decay. And I tried to run all of that with just those 5 summary statistics, but it turned out that the data set, that this type of data is quite intricate, and we needed really to throw the kitchen sink at it. And it turned out the things that worked were that when we take the inter-event times, we take the ones that lie above the 90th quantile and take their average. And we do the same for the inter-event times that lie below their inter-event time median. Now, this is not intuitive anymore. I've worked on Hawkes processes, and I cannot really tell you why these seem to work so much better than any other. And this, I think, is really the tricky part when it comes to using approximate Bayesian computation, is to come up with summary statistics or to come up with a way of comparing two data sets to decide when are two data sets actually close enough that we're going to accept the generating parameter as a draw from the posterior distribution. So this is the tricky part. Let's look at a little example to hopefully lighten the mood a little bit. It turns out that another data generating process that follows this Hawkes type of behavior are retweets on Twitter, or nowadays X. So if I follow Chris and Chris tweets something, then I'm a little bit more likely to also tweet, because it might be a retweet from your lovely tweet about a new RSS event that I really want to attend. So this is something that is actually behavior that appears in person, so that appears in reality. So these are retweets of a New York Times article. So the first article was tweeted, and then we record all the retweets. So I suspect probably somewhere around here, someone with a lot of followers retweeted again. you could already imagine all the things that you could do here. You could have a covariate of how many followers does the person have, who retweets it, do they have a private profile, whatnot. So this is a complete data set of real world data. And what I'm going to do now is that I'm going to take out a few events in the middle, all that are in the gray shaded area here, and delete them as if they were not recorded. But I still have access to them to compare to the ground truth. And we want to really see what can we do with that. So we're going to run this whole ABC procedure that I had mentioned earlier and see how close do we get to the actual truth if we just ran your run-of-the-mill R-stan model on the whole complete data set. So we have an example where we can actually compare to the ground truth because we have the full data set. And what we see is that it's all right, in all honesty. So let's go through this one by one. The thick black line is the truth if we calculated, if we got the posterior distribution of the full data set. If we were naive about it and just forgot the fact that there is a gap in the data, obviously we'd be massively off. Interestingly, the background rate, obviously by far the most affected because we've got a lot less data in the mix. But interestingly, the decay is actually really well estimated, which I found quite interesting. But if you think about it, actually that does make a little bit of sense. Okay, so we've got two more lines remaining. We have the blue line, which is the model that I've just presented, or the approach that I presented, and the other one is a competing approach that does something with imputation. And I would say they are probably more or less similar. If you look at the standard deviations, they're probably almost exactly as good as each other. So maybe here the blue one's a little bit more accurate. Here, the yellow one's a little bit more accurate. Here, this one's underestimating, we're a little bit overestimating. In general, ABC will often overestimate the posterior variance a little bit because we have to set some type of non-negative epsilon to say how far away do we allow the closeness, how close do things have to be to accept? That cannot be zero. They can't be exactly the same. And that leads to an overestimation of variance. So on here, I would say this is a pretty even Stevens between the two competing methods. What I do have to say is that our method actually allows you to do a whole variety of deletion processes. So you might see a constant deletion across the time. You might see like a step function. And our method allows you to do all of these, and the competing method only allows you to do the gap method. So I would say we're doing better than a naive, as good as state of the art, but we can do a little bit more than that existing method. And I think that's a really neat way of dealing with a problem that people might actually have in practice. And this brings us now to how can you actually use ABC when you think of a Bayesian problem that you are encountering. So let's get through the things. What do we need to do? Sample from the prior, generate synthetic data, calculate summary statistic, define a distance, accept, reject. Cool. We could be done here, right? That is basically the end of the talk. No. We're going to walk through now each of those bits, bit by bit, to really take a look in detail. What do those things actually mean for you in practice if you wanted to do this? So let's go through these one by one. Sample from the prior. Now, as we have already heard in our quiz earlier, a prior is something that you choose. So I would highly recommend choosing a prior that you can sample from. These are all your classic things like a normal distribution, a beta distribution, whatever it is. You're probably going to choose something that you can sample from. And in most cases, you can probably do this in base R. So I've just, as a kind of pseudocode, I've just used a normal distribution here. This seems like an easy step because you have a lot of choice in that. We're then going to come to simulating a synthetic data set. Now, I've colored this green, and this is very pseudocode, simulate data. This really depends on your issue. I suspect that if you work on a complex problem, you have already figured out how to generate synthetic data for your data generating process. But this is quite complex. if this part involves the likelihood having to be evaluated, ABC is probably not the tool you want to use, because if you can evaluate the likelihood, maybe don't go through all of this business here. So hopefully you have a way to actually simulate from your data without the likelihood. So for now, we're good. So we can sample from the prior and parameter theta star, and we can get a synthetic data set y star based on that parameter. Cool. Now it becomes difficult. Now we have to decide how to find those, what those summary statistics are. So we're gonna have S here is our summary statistics from our real data, and S star are the ones that belong to the synthetic or proposed data set. And what those are, that's where it gets tricky. And I think that there is some really interesting theoretical research out there on approximate Bayesian computation that always assumes that we have handy summary statistics that just fall out of nowhere. And I think that is where it really gets tricky, because it requires domain knowledge. And it requires, as I've experienced, lots and lots of simulations to really figure out what does it mean for a data set to be different. Now, you might encounter actually an issue, and you might be quite lucky that this is something that really matters in practice, that there are quantities in your model that you can understand from a human point of view that matter to you. And maybe actually this is not the hardest part. Hopefully calculating them is easy, but deciding what they are is actually quite hard. I've just put in here length as some type of summary statistics, but this is actually the hard part. Again, so for this, you're probably gonna be able to deal with base R. Here, this probably requires quite a lot of custom code, but I suspect you already have that written. This requires a lot of thinking about those summary statistics, but if you're lucky, you're probably going to be able to implement them once you have chosen them quite easily as well. Now we need to find a way to compare those summary statistics. Are we going to use, are we going to do squared? Are we going to do absolute? Do all summary statistics have to be below a certain value? Or do we take a median? What do we choose here? Again, there's many ways of doing it. And I'm sorry to say, there's not really one right way of doing it. So it might depend on your application. I recommend here doing lots and lots of simulation. Pick two parameters that you would want, that are far enough away that you would consider it important to distinguish between them. Simulate a whole lot of data sets. Look at the summary statistics. Do they differ significantly or not? That is how I came up with those scary 7 ones that I showed earlier. And if you have all of that, there's one last bit left that you have to do. And that is find an epsilon value that you accept, such that you accept theta star as a draw from the approximate posterior distribution when those summary statistics or the distance between them is below that epsilon value. You could do something that maybe you want to generate lots and lots and lots of samples, and potentially you just want to accept the best 10% of them. But again, there is a little bit of trial and error left in that. But hopefully, when you've made all these three choices, actually implementing it in R, you're probably going to get away with doing it in base R with just a little bit of code yourself. There are great packages out there, and it's a real shame that our second presenter today is not available, because he would have gotten in all of that. So when that talk gets rescheduled, please do attend. I will certainly. So where does that leave us? ABC is a tool for an approximation of the posterior distribution. I think you can really use it if you can't evaluate the likelihood, or maybe you just can't be bothered writing down the likelihood. I think of data generating processes that are quite complex. Maybe there's lots of decision gates. I think of maybe people going through different processes and arriving at the end at a certain output. Those are all things that I have very high confidence that all of you could write a quick bit of code to generate synthetic data from, but it would be much trickier to write down actually the likelihood of such a model. So there are cases where, yes, we can find the likelihood, and it's a perfectly normal likelihood. absolutely not intractable, but maybe it's just a little bit cumbersome to come up with it. And it might be just a nice and quick and dirty way to do Bayesian statistics, or to look at the data from a Bayesian point of view. There's a lot of research out there on ABC and how it can be improved. But as I said, finding those summary statistics is, from my point of view, downplayed a little bit. And in practice, it may be difficult to find those summary statistics. Or you're lucky, you are in an environment that you've got ideas what you're gonna start as summary statistics in your trial. Once you have made those choices, it's actually quite easy to implement in R, and you get samples from a posterior distribution, and that allows you to do all the fun things that we know how to do with samples from posterior distributions. And that has been hopefully an interesting and useful introduction to ABC, Approximate Bayesian Computation, but also a little bit on point processes in the Hawkes process kind. Thank you very much for your attention. I'm really excited for your questions. And if you ever want to get in touch, here are my contact details. Thank you very much.
Thank you, Isabella. That was great. Does anyone have any questions for Isabella? Yeah, I can bring you a microphone. Yeah.
Very interesting. Just was slightly puzzled. Does it not matter about the sample size when you're choosing epsilon? Is it completely irrelevant?
Do you mean by sample size how many synthetic data sets we generate?
If you choose as a statistic the mean or something like that, then obviously the variance of the mean will depend upon the sample size. So even if, in some particular cases, even if you had the parameter estimated very, very well, you would find that repeated draws from the same parameter setting with that sample size would give you very, very different statistics.
Yeah.
Is that completely irrelevant problem? It all comes out in the wash, or is it something you have to choose depending on how many data you have?
So if for the same parameter, you get the variance between data sets is very large, that is an issue. That is certainly an issue. And that relates exactly to that epsilon that you have mentioned. So unfortunately, ABC doesn't automatically take care of that. You can potentially see if you can rescale some of the so there will be a lot of variance in your summary statistics, even if they come from the same parameter. It's probably not best summary statistics. So it doesn't take care of it, but you can keep looking and maybe you find a summary statistic that doesn't have that undesirable property.
Thank you. That was really fascinating talk about something I vaguely heard about and always wanted to learn. You don't have a likelihood, but you still have to have parameters.
Yes.
Because you have to have parameters to put priors onto.
Yes.
And I was just having an out-of-the-box thought, which is probably rubbish, but could you, instead of putting priors on the parameters, put priors on your summary statistics?
So we do have a likelihood. I can write down a likelihood using my parameters. I just can't evaluate it.
Yes. Okay.
So
you really can't get over that. Okay.
Yeah.
Yes. I mean, the reason I find it really interesting is that I work on creating synthetic data, but that's very different from what you're doing. You're doing it from a model that you know the parameters of, whereas I'm trying to do it from data that we actually don't know the distribution of. I think I'd love to speak to you later, because I think some of the things you're talking about could map quite interestingly, because what we try to do is we try to devise what we call utility functions to see how well our synthesis has worked. And so they're a very bit like your summary statistics.
That seems very similar. Absolutely.
Which is really
I'd love to have a chat afterwards.
Yes,
absolutely. Yes. Please.
Really great talk. Thank you.
Thank you so much.
Thank you. Anybody else? Yes, go on.
Very nice talk. Thank you. I have a question about how you compare the synthetic data and real data. So in your approach, you are compute some statistic and then compare that statistic over the synthetic data and the real data.
Yeah.
So I wonder, have you considered about calculating the empirical distribution and compare the KO divergence or some CRPS?
Yes, absolutely.
So what's the drawback of using this approach and why you don't use it?
So instead of summarizing the synthetic and real data set into summary statistics, 7 in my case. You could also just look at empirical distributions, but of what? And I think that is the question. The empirical distribution of what? And in our case, maybe you could look at the empirical distribution of the inter-event times, and then you could calculate the KL divergence or the Wasserstein distance or whatever you want it to be between those two distributions. Or maybe you want to have a histogram and you want to compare two histograms. Yes, you can do that, but I think it lends itself much better to data that lives on a continuous scale. We have this challenge that we have this weird event time observation. So yes, it works. There's great papers out there. I tried it on the inter-event times, and I found that for this particular type of data, it really didn't work well.
Thank you.
Thank you.
Anybody else? So this one, this one.
Yeah, thank you so much for the great presentation. I was really interested when you showed the imputation of the missing data. Is that sensitive to the type of missing data? Does it depend if it's missing at random, missing completely at random, or is it robust?
That's a really good point. So my first instinct would be that as long as you know what type of missingness it is, you're good to go. As long as you can easily recreate it by, in my case, taking everything that's in the gap and throwing it away, as long as you have a way of recreating that missingness, I think you should be good to go. Thank you.
Here. Yeah, I was also wondering about the, first of all, thank you for the excellent talk. I was wondering about the examples you showed where you are throwing away missing data. Is there a point at which, or have you looked at the effect of throwing away more or less data? And does your choice of metrics that you're choosing to compare the data sets change depending on how much data you've got missing? And is there a point at which you've just got too much missing and there's really nothing you can do?
So yeah, absolutely. That is something that happens in real life. And yes, I've looked at it and it's exactly how they expected it to be. The more there is missing, the worse it gets. So I think what the model needs to learn is this: how many events happen after an event happened. So one big gap missing in the data is not great, but having lots of gaps in the data that maybe are smaller than in total a big gap, that is actually worse. And so this is, I think, is about 25% of data missing. That was pushing the limit, I think, where we could comfortably get to. It is, so Hawkes processes in and of themselves are already a weird and somewhat difficult thing to work with. We're just piling something more difficult onto something already quite tricky.
So I just had an extra one on choosing the distance parameters. When you say that's really difficult to do, is it just kind of taking educated guesses at what might work and simulating, like you say, or is there some process you can follow to say, well, this one was okay, therefore this one might be a bit better because it's similar in a way?
So I wish I could say, yes, there's a great way of doing it, but I haven't found it. And if everyone does, please tell me, because it was a lot of letting all your simulations run overnight and then coming back in the morning and seeing what happened.
It was a great talk. So for the whole process, was it that you were using like 6 or 7 summary statistics? So I guess, is there like a rule of thumb in coming up with just a number of or different kind of summary statistics?
So there's a rule of thumb that you should use about as many summary statistics as their parameters.
I see.
Yeah. I would maybe caveat that with the same order of magnitude.
And well, I guess supposedly then for neural network, I guess then would that be a bit too much if you want to do that? Because apparently it's very difficult to evaluate likelihood for different neural network kind of their likelihood stuff. Yeah.
So do you encounter the issue that you have a likelihood that you can't evaluate in that case?
Yeah.
Okay. I think maybe there are some statistics, but because there's so many parameters in a neural network, that is what makes it great. I'm not sure if that is the right way to do it.
Yeah. Okay. Yeah. No, thanks.
Any other questions? Okay.
Thanks. Am I right? The approximation in ABC is that you're assuming that your distance metric maps onto the likelihood, and therefore you can do rejection sampling on the distance metric instead of the likelihood.
So there's some great papers or some great research out there that says if you have sufficient statistics, then your approximate Bayesian, that is what you get out of all of this. And if you use your sufficient statistical summary statistics, you get exactly the posterior distribution as your epsilon becomes smaller. So, but I'm not sure what happens when you don't have sufficient statistics. I think that is where things get murky.
Conceptually, there's some hyperparameter sort of things which map your distance metrics to the true likelihood, which you're assuming don't exist, but they're really that's the catch, really.
I think that is what it feels like. Yeah.
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 Nice. Thanks.
Thank you.
Yes, thanks for the talk. One thing I'm wondering about is how will this approach kind of tell you, are there tells if given the amount of missingness and given the observed part of the data generating process, it's suggesting it could be resolved in a multimodal way. It would either be this set of parameters clustered over here, or it will be this set of parameters over here. And both of those lead to similar rates of acceptance. Are there sort of tells for when, given the amount of data, it's ambiguous, but it's not infinitely ambiguous. It kind of clusters, the parameter space kind of clusters around 2 or 3, points in whatever the k-dimensional parameter space is.
So I've definitely encountered that in my experience, that sometimes there are 2 parameter constellations that are very similar, that produce data that is very similar. And again, similar to true data. So yes, that can really happen.
Thank you for the talk. So at each step, you generate your parameters from the priors, but if the priors are really bad, surely this is really slow.
Yes.
And especially if you've got high dimensional data, surely this is just really, really slow.
So yes. So the first answer is yes. If you do it just like this, you're absolutely right. If you have a very high dimensional space, well, if you've got very many dimensions, maybe ABC is not your method of choice, but let's say you've got an appropriately large size of dimensions, this is going to be slow, completely with you. Luckily, there are some neat little tricks that instead of sampling from the prior, we get an MCMC update in here. So if you had a parameter accepted, the next parameter is not anywhere in space, but a little bit further away, and you get an MCMC chain through the space. Doesn't make a huge difference. That you need to then think a little bit better about what does it actually mean to accept, because you can't just do all your samples and take the best 10% at the end. MCMC doesn't really do that because you need to accept a parameter to suggest the next parameter, but there are ways around that because as you very correctly identified, that would be a big issue if you've got a very flat prior.
Thank you.